This is homework 5 part C, right? We're going to be talking about heat exchangers, co-current and countercurrent, right? So what I've drawn here, right? This is a co-current heat exchanger, right? You have your hot temperature going through the middle here, right? And then you have your cold temperatures on the outside going in the same direction. That's co-current. Countercurrent is when uh, the hot and the cold are going opposite of each other, right? Um, and that typically is the more effective way, but we are going to see why today, right? So when we're looking about trying to figure out the amount of heat transfer there is, right? The equation we would use is Q equals U, which is a uh, universal heat transfer coefficient, right? Multiplied by the temperature difference, TH minus TC, times the difference in area. But this isn't super helpful for us because we don't know how the heat or the temperature vary with area, right? So one thing that we can use is a mass flow rate heat capacity. And so what this is the mass flow rate of one of your streams, so let's say hot, multiplied by the heat capacity of the hot stream, right? And so this can be written as CH, right? And then the same thing for cold, right? So M cold times the heat capacity of cold equals, these are flow rates, the CC, right? And when we're looking at this, we can remember something from Gen Chem, which was Q equals MCAT, right? Q equals the mass flow rate times the heat capacity times delta T, right? MCAT. Well, if we look at this, this is just this but unspecified, right? So if we're looking at it in terms of uh, in our terms here, right, we can rewrite these, right, as first we want to take the derivative, right? So dq equals mcp delta t, right? And so when we do this, we can see that we can do dqh equals mhcph delta t, which is just dq equals this c hot dt. And the same thing can be done for the cold, right? cc dt, right? And we can use this, right, um, by rewriting this original equation, right? So it'll be Q equals and for the hot, it'll be negative. So negative CH, and then it'll be your delta T, right? That's going to be T hot 1 minus T hot 2. And then the same thing for the cold, right? Q equals CC TC 2 minus TC1 because it's hotter um, when it's coming out, the colder one is. Um, and so from this, we can move on and we can go back to this equation up here. Um, right, if we take this derivative, we get dq equals u and then d delta t dA. Um, and when we do this, right, uh, well, first we want to make sure we specify the change in temperature here. But when we do this, we can rewrite this, right, as dt delta t equals dth minus dtc. And we know where we can figure out what these dth and dtc is, right? Because we have it here, right? So this can be rewritten as dq over ch minus dq over cc equals d delta t, right? And um, with that, um, that dq can be factored out, right? So dq 1 over ch minus 1 over cc equals d delta t, right? And then we can plug this back in to this expression here and solve for d delta t. And when we do that, we get d delta t equals u 1 over ch minus 1 over cc dA um, with our delta t in here. And then this is just a separable equation that we can rewrite as 1 over delta t d delta t equals u times 1 over ch minus 1 over cc dA, right? And then we can integrate both sides. And since our ch and our u don't vary based on area, right? Those are constant. So all we have here is u a times 1 over ch minus 1 over cc, right? Um, and with that, and then on the other side, we have our natural log of, it'll be dt2 over dt1, right? And so here we can then plug in our values, or we can take out these values and put in the values that we would get by solving for them here, right? And so what we would get is dq over tc or dq over th, right? And so when we do that, we get the natural log of delta t2 over delta t1 equals u a, and then right, it'll be th2 minus th1 over q, right, minus th or tc1 minus tc2 over q, which then we can factor out the 1 over q and get ln delta t2 over delta t1 equals u a 1 over q times delta th minus delta t cold, right? And then we can solve for q, right? So when we solve for q, what we get is q equals the u a, and then ua, and then delta th minus delta tc, right? All over the natural log of t2 over t1, delta t2 over delta t1, right? And this right here is your log mean difference, right? Which is used to calculate your overall heat transfer, which is what we were trying to find in this question, right? And so when we look at this in the realms of countercurrent versus co-current, right? So co-current, right? You have position 1 and position 2, right? Your hot stream starts here, your cold stream starts here. And as you go along, they converge, right, to a certain delta T, right? And that then limits your overall heat transfer. But if you have countercurrent, right, your cold starting down here, your hot starting up here, your cold will get a little bit warmer as you go, and then your hot will not will result in a greater delta T, meaning that you have more heat transfer when you have countercurrent, and eventually this will get down to the level exactly of your inlet cold, right? And so that's not something that ever happens here. This will just carry on infinitely, never getting to the temperature of the cold, and they never intersect. This will then get down to your T cold, right? that you want it to. And so you'll have greater heat transfer overall, right? So your Q will be higher, right? And that makes sense because when your TH is higher, right, you're going to have a larger value here. Like, right, because you have your TH here and your T2 here. When that's higher overall, right, your overall Q will be greater. Next, what we'll talk about is how effective a heat exchanger is, right? So the effectiveness of a heat exchanger is determined by the heat transfer versus the maximum amount of heat transfer, right? And so when you're looking at a heat exchanger, this can vary based on the speeds of your flow. So if you have a cold stream that's going slow and a fast hot stream, that's going to have um, a greater heat transfer because your uh, your hot stream is mixing with a colder stream over like more constantly, and so it'll have a higher um, heat transfer, right? And so when we think about the flow rates, right, we can rewrite this equation, and so the flow rate that you have going, uh, right, the flow rate that you have multiplied by your T hot out minus your your T hot in minus your T hot out is your total Q, right? And then your maximum Q is going to be when your flow rate is the lowest, right? So you will have a Cmin value. And then that will be multiplied then by your T hot in minus your T cold, your cold in, right? And this is for your hot stream, right? And so if you're looking at it for your cold stream, right, you have your CC T cold out because that's the greater temperature minus T cold in over your minimum flow rate times T cold in minus T hot out out. And so no, sorry, that's wrong. This should be still T hot in minus T cold in, right? And so we look at it and we kind of get a value, or we get a more approachable equation for our effectiveness of a heat exchanger, right? And then with this, we can relate it to our NTUs, right? And so what an NTU is, that's a C. An NTU is the net transfer units, right? And this equals our UA over C min, right? And so, right, this is a value that can be that will be pretty much given to you if you buy a heat exchanger or your company has a heat exchanger, right? You're going to have these values, and so when you're looking to maximize the NTUs, right, all you have to do is vary this flow rate or figure out this flow rate to determine what your maximum NTUs would be, right? And so that's another way you can work with effectiveness with um, with your um, heat exchangers, and the C maximum value would then be where the maximum amount of flow rate you can have before your heat exchanger is no longer effective, right? And so there, there's always going to be a minimum value, but oftentimes you don't think about they're too fast or too much of something. But in this case, too fast of a flow rate would impact your overall heat exchanger. So that's kind of how effectiveness works with NTUs and effectiveness in heat exchangers. And then over here, right, we talked about co-current and counter-current and how those differ and how we were able to, I didn't write this down, find the log mean difference, right? And that's a very common thing, right? When you're looking at heat exchangers. And so that shows you kind of why countercurrent is better than co-current. So that was homework 5 part C.